Anyway, yeah, so that is
Yeah, but I'm not around there.
you're here, right? So you're off, right?
Yeah, I'm up for the year, yes, I'll be Francis.
Oh, cool. Where are you going?
Francis Fest.
Oh, with France.
Now.
Otherwise, right.
So my stream is but with most speakers.
Oh, oh, here.
You use your this is fun. That's great, right? You do not want your language to be used in. But it's nice for people who are online to see that there's yeah.
All right, so welcome everyone. I think we've got all the streaming under control now. So welcome to the Simons Institute. My name is Peter Bartlett, I'm the Associate Director. And welcome to the workshop Sampling Algorithms and Geometries on Probability Distributions. It's the first workshop for the program on geometric methods in optimization and sampling. I'm very, very happy to have you here. A big thank you to the NSF for its support of this program through the Foundations of Data Science Institute. Big thank you to the organizers of the workshop, excuse me, Diakonikolos, Philippe Rigolet, and Santosh Vempala. So big thanks to them. So I'll hand over to Jelena in a moment, but let me just go through a few logistics first. You've discovered the food outside for breaks, food and coffee and so on. Please don't bring those into the auditorium, and we'll have those at the various breaks throughout the day. For lunches, you'll be on your own. Please wear masks inside. I'm sure you've seen that request. For lunchtime and any other time, I guess, you can leave things in lockers on the far side of the building on this level. There are PIN numbers for those lockers. Everything's in a hybrid format, so we've got everything streaming on Zoom and YouTube. And Darren here is helping out with hooking up speakers, computers and so on. And also, big thank you to Ashley Hassan back here, who managed all the local arrangements for this workshop. Thanks a lot. All right, so enjoy the week. Looks like a fantastic lineup.
Thank you, Peter. Hi, everyone. Good morning. I am Jelena Diakonikolos, and I wanted to wish you a welcome to this workshop. I want to start by thanking my co-organizers, Philippe Rigolet, who is right here, and Santosh Vempala, who will be here later this week. We also got great support from the Simons Institute to organize this, and specifically from Peter, Christine, and Ashley. They helped a lot. So we have prepared, I believe, an interesting schedule. There's a little bit for everyone. So the topics range from more traditional theoretical computer science work that is more on the random walk side, over Langevin dynamics, Hamiltonian Monte Carlo, particle-based sampling algorithms, and even talks that are more on the side on geometry of probability distribution, so not necessarily about sampling. We will also have a few talks that are more applied. This is quite intentional because most of us here are theorists and we tend to work on proving all these computational bounds without thinking much about where these problems come from. So I think it's going to be fun to see these talks. There is at least one on each day, Wednesday, Thursday, and Friday. Okay, so one brief announcement. On Wednesday, we are going to have an open problem session. So please think about open problems you would like to share with others. And the understanding is if you share a problem, that people will come and talk to you about that problem. There are lots of breaks in the schedule, and that's also very intentional so that you can easily context switch between talks. We are running a little bit late with the first talk, but in general, I would like to ask the speakers and session chairs to make sure that for other talks we try to be on time just so that people can talk during the breaks. Okay, so it is a special pleasure to start this workshop with a talk by Ravi Kannan. As many of you know, Ravi has made many seminal contributions to theoretical computer science, but in the context of this workshop and this program, Ravi was one of the pioneers when it comes to computational guarantees for sampling algorithms, in particular for random walks. Back in the, I believe, late 80s, early 90s, Ravi worked on using random walks based sampling algorithms to develop a polynomial time approximation scheme for approximating the volume of convex polytopes. Now, this is a very interesting thing because those problems are computationally hard to approximate with deterministic algorithms. And what Ravi, alongside Dyer and Fries, shown was that if you use sampling algorithms, you can actually do this in polynomial time. Of course, polynomial in 1 over epsilon 2. And for this work, Ravi and his co-authors received the Fulkerson Prize. So it is amazing that he's here to open this workshop. He will not be talking about random walks, but about clustering problems. And the title of this talk is How Many Clusters an Algorithmic Answer? Ravi, thank you once again for being here. And please all welcome Ravi Kannan.
Thanks for the intro. I'm going to talk about something a little more recent. That this is last year or this year, but there'll be, actually said there'll be other talks, survey talks later in the week. Right? So there's a question of how many clusters there are in a clustering problem. That's the title. And we will give an algorithm to find the number of clusters. This is joint work with Chiranjeev Bhattacharya and Amit Kumar. I'll introduce the problem and why it's interesting first, and spend a fair bit of time on that. But the clustering problem we have in mind is the following. I mean, there could be several versions, but this is the version we have in mind. First of all, you have endpoints in Euclidean space. Distances are measured in Euclidean space, right? In RD, D is a dimension. And we are promised, this is what's called a promise problem. We are promised that there is a nice, and I'll define nice, there's a nice ground truth clustering C1 through Ck, because we don't know that clustering. Our job is first to find K exactly, and this is already a departure from most literature where K is assumed to be given, a point that I will come back and stress. And the ground truth clustering approximately. Approximately means a small fraction could be misclustered. But K, I insist, should be exactly found, right? No plus or minus 1 even in the answer to K. So data generated by stochastic mixtures, which is relevant to this workshop, and I'll come back to those, is something that fits this model, where the ground truth is which component of the mixture you use to generate that particular data point, right? So data points are clustered by what component, if it's Gaussians, which Gaussian that you generated the data point from. Our results are general and don't assume a stochastic model. So we'll assume will involve no stochastic model, only deterministic conditions. But they will include as special cases, Gaussian mixtures, in fact, all log concave PDF mixtures and others. And I want to stress that previous polynomial algorithms, generally, there may be some exceptions for special cases. Generally, even for special cases, even for Gaussian mixtures, assume K is given, right? That's our first point of departure. I won't introduce a lot of notation, but I introduce mu and sigma. Mu and sigma now, without reference to probability, just for any set of points, mu is just a mean, centroid, if you will, just the average of all of them coordinate-wise. And sigma is a standard deviation, maximum one in a 1D projection. So you take all 1D projections, take the worst spread, and that's your standard deviation of the set. Okay, so these are the two pieces of notation that you should remember, mu and sigma, they're standard. So the importance of knowing K in general, what's done in a lot of literature is K gives you an objective function, like K means, K center, there are many of them. K gives you an objective function, and ever after you specialize, you focus only on optimization. So it's a nice, clean mathematical problem, and you optimize, but then you have to be given K. So K is crucial for that. It led to a lot of nice algorithms, of course. We have a lot of literature on that, including Lloyd's algorithm and beautiful heuristics for K center. Now, more recently, we know now, this is due to Wempala and Wang first, that for Gaussian mixtures, I guess I'm not defining mixtures, you're all familiar with that. It's just the probability function is a weighted combination, convex combination of various other probability, various Gaussians, right? K Gaussians in this case. So if I tell you something is a mixture of K Gaussian and I give you K, then you can project down to the K-dimensional singular value decomposition space. If you're familiar with what SVD is, this will make sense. Otherwise, don't worry about it. It won't actually impinge on the understanding of the main points. This is what the literature does, right? And then you can work in the projection and cluster. That's known, but you need K at the outset to know where to project. Okay. And other results show that, in fact, you don't need stochastic assumptions, even under deterministic assumptions. Still need K. There's another class of algorithms, which is distance-based clustering. And I'm going to state it very roughly. This is only a generic statement. There's some tau, which is a threshold, and points at distance tau from a data point, or quote unquote cluster mates. They belong to the same cluster as the point. And you use this to classify. Lots of bells and whistles. This is just a generic, simple statement. You need tau, but you don't need K in this setup, right? You just take tau as your cutoff, and then you get clusters. But unfortunately, this does not work even for the case of a mixture of two standard Gaussians, means a constant number of standard deviations apart, right? And it doesn't work because inter-cluster distances and intra-cluster distances get confused, right? Points, your cluster mates may be farther than points belonging to other clusters at this separation. It's a simple thing to work out. So even though distance-based clustering is used, it's often used assuming a huge separation between means, a point we'll come back to. Okay? Not this kind of 6 standard deviations or constant number of standard deviations apart. Now, for Gaussian mixtures, there's been a lot of beautiful work pinning down the exact separation, the exact sample complexity, and so on. I quote a few, but there are many more, but they all need K, even for spherical Gaussians. So there may be exceptions that some of you are aware of, but I'm not sure in any generality. We can later discuss that, but generally they all need K. I'm spending a fair bit of time on motivation partly because the technical details are complicated enough. They'll take too much time. So, but anyway, I will get to the theorem. I'll state it precisely. I won't give you all the proof, but I'll give you ideas later. but still we are continuing sort of on conceptual part of the talk still. So the first assumption for niceness is there'll be other assumptions you'll see. Mean separation. For every cluster in the ground truth, we assume the mean of other clusters is a constant. Star is polylog factors. Constant sigma of the cluster itself away. It's very important through the talk that I'm going to measure distances by quantities that I can learn from the data. So sigma is the unit here. Sigma is going to be the unit of distance quite often, but sigma of that cluster itself. Okay. So if I gave you the cluster, you can find sigma. Sigma, by the way, is a spectral norm calculation. I didn't say that, but sigma can be computed. I give you a set of points. It's the calculation of a spectral norm of a matrix. Okay, so means of other clusters, or at least so many standard deviations away. Most precisely, this is the bound we assume with some log factors there. And this factor, W naught, is the min weight of a cluster. That's always there in most cases. Because if you have a very small cluster, it better be very far, otherwise you'll confuse it with other clusters. That's standard in all the separations used. So here's a little picture that's good to remember. Two Gaussians, omega sigma apart. The thing to notice is data points are at distance root d in d dimensions. If sigma is 1, right? Sigma is 1, then they're root d away, but the separation is very small. This is a picture to remember, schematic. The separation is tiny compared to the distance of the points from the center. D is big. We'll assume D is big. We are doing asymptotic analysis when D is very large. So this is typically something you better be able to cluster. So the other thing that's happened about K is there are many heuristics that infer K from the K means cost by plotting how the K means cost looks as you go up on K. So the K means cost, for instance, goes down as you increase K, of course, right? How it goes down, you plot that, and then you try to figure out K. There are several ways of doing that. Perhaps the classic method is by, for instance, Hartigan, I think it's in the 70s. Take the biggest drop as you decrease K. It's called the elbow method. There's no general proof, and I, in fact, tell you that that doesn't work even for simple cases. Now, under the assumption of a big drop, we can find the clustering. There are theoretical computer science results, but these big drops are not present in general. The amount of drop they want is not present in general. There's a related thing sort of called gap statistic, for which we do have some proofs. It takes the ratio of the K means cost to the 1 means, but it needs a prior, and analysis is only known for certain things like special Gaussians, right? But here's a little fact to remember. I won't give you these examples, they're in the paper. Even for spherical Gaussians, it's not true that the largest stop occurs at the correct K. In fact, for every integer, there is a mixture with that many components, but the largest drop occurs at K equals 2, and this is even for spherical Gaussian mixtures. Again, I won't give you the example, it's in the paper, but so you can't go, the elbow method doesn't work even for spherical Gaussians in general. Okay, so here's an example, just to bear in mind, one big Gaussian, they're all Gaussians, let's say, one big Gaussian, small Gaussians. These are separated by units, sigma units, right? And this is very large sigma, C, and these are separated by C units. So it conforms to mean separation. Now, the $1,000,000 question here is K2 or is K7, sorry. The 6 plus 1, 7. Both are reasonable solutions. So what's K? Okay, so we'll come to that. So conditions for nice ground truth. So we had mean separation. That's not good enough because putting every point in a single cluster by itself is consistent with mean separation, right? If I put a single point in a cluster, it's sigma 0. So you don't require any separation. And so that's consistent. We don't want that. We don't want to split points up. We want some sensible lower bound. We'll have a lower bound in terms of data. I put an arbitrary exponent here, but n to the minus 0.1 is also all right. Some polynomial in n, minimum weight assumption. Now, is that enough? Minimum weight and separation? No. K equals 1 is still a possibility. If you have one cluster, mean separation is empty. There's no other cluster to separate it from. And so that's legal. And min weight is true because I put everybody in one. Okay. So if you want even to be able to tell what K is from the data, even in not polynomial time, even in exponential time, it won't do just to have these two assumptions. We'll have to add one more, and that's a crucial assumption. We'll see. So usual fix, as I said, assume K is given. So this is a second time I'm stressing this, but I'll not do it anymore. Theoretically, K being given helps in the following ways. It helps you define the objective function as we saw, and then reduce to optimization. Now, K being given indirectly defines what a cluster is, which is sort of unfair, it would seem, right? It's sort of cheating in some sense. K is an extraneous parameter which says number of clusters. That tells you what a cluster is. In this example, K is 2 makes all of these cluster mates into one cluster. K is 7 makes them all split up. So your K defines what a cluster is, which doesn't seem fair because K is just an extraneous parameter you gave it. Okay. And we show in the paper, and it's not very difficult, that in fact, getting K is NP hard, even within very large factors, because coloring is reducible to that. Again, I won't do that. Practically, how do we know K? Okay. And the worst part of the deal is in TCS talks, people don't worry about this. In theoretical computer science, data is somebody else's department, so they have to give us the data and we can process it, but we don't care about how the data comes, right? So, but people ask, non-TCS talks, people always ask me, how do you get K? And the answer is, I didn't know so far, but this is meant to address that question, right? Okay, so now I want to tell you the important, crucial third condition I want to introduce by this very simple picture. So suppose I tell you the null hypothesis is one Gaussian, D equals one dimension on the line. I give you data points. Null hypothesis is one Gaussian. The H1, the alternative hypothesis is two Gaussian, mixture of two Gaussians, equal weight, right? How do I tell the difference? There are a zillion ways to tell the difference for Gaussians, but here's one way that I am going to use. I take the PDF at every point of the mixture. That PDF here, if it was one Gaussian, would be at most 1/2 pi square root sigma, right? That would have been the case if it was one Gaussian. But in the alternative hypothesis, this height is much higher than the sigma of the whole thing. Because sigma of the whole thing involves the separation, right? Half the mass here, half the mass here. Sigma is at least as much as that. So sigma has gone up a lot, but this remains 1/square root pi the old sigma. So the PDF is very, very large at some point of the mixture. If it was two Gaussians, if it was one Gaussian, it wouldn't be large. If it was one Gaussian, it's always going to be at most 1/square root 2 pi sigma, at least for Gaussians. Actually, it's also true for log concaves. We'll come back to that. So this is going to be the definition of anti-concentration. Anti-concentration rules out your thinking this example was one Gaussian. I want to rule out your thinking this is one Gaussian, whereas it was two, right? So that's anti-concentration. A set S of points satisfies anti-concentration if the following is true. So I want to translate 1/√2 pi sigma for PDFs into empirical statement about a set of points, right? So that's what this is doing. So if I take any line and project to the line and take intervals that are not too small, the most important point is this. The number of points in the interval is proportional to the length of the interval at most times sigma. Okay. This is true for a single Gaussian. Yeah. Okay. And it's not true for the pair of Gaussians well separated. That's just the empirical version of the last statement that I made. By the way, I have to take large enough intervals because since I have a point masses, if I take a very small interval, this is not true. This is the projection. Clustering is finally nice if each cluster has anti-concentration. Each cluster has this behavior and mean separation and minimum weight also hold. And the first theorem is identifiability. The main theorem is an algorithm. So what is identifiability? Let me backtrack one step. It's a familiar notion in machine learning. Usually identifiability just means that the data, only the data is enough to tell me what the answer is. The answer I want to know is K. K is exactly determined by data. This is the number of clusters. So there cannot be two clusterings with different number of clusters, which are both nice. That's the first statement. And furthermore, there cannot be two clusterings with the same number of clusters, which are very far apart. Here, the distance is Hamming distance, is how many points you must recluster to get from one to the other. So this says basically there's a unique, nice clustering. There's at most one nice clustering. There may not be any nice clustering. There's at most one nice clustering for any data. Yeah.
So that should also depend somehow on the number of points.
Number of?
Points that you have in your data, no?
Yeah. So the minimum weight tells you the number cannot be too small. But beyond that, no. When we come to stochastic models, yes, we need a sample lower bound. We'll come to that. These are not stochastic, it's all deterministic. So it's not a hard theorem. It takes a few pages, but it's not immediate. But so identifiability theorem says K is pinned down by data, no additional information needed. That's what identifiability means. Paper also polynomial time algorithm, which is the main result. We'll come to that now. Everybody with me? So point-wise upper bound on PDF or empirical version of that. So the algorithm is harder. There's another property I want. Oh, sorry.
I just wanted to understand somewhat the geometry of your definition of the cluster a little bit where it follows. Am I correct in kind of concluding that this assumption included in itself somehow that geometrically they kind of have to be roundish? Namely, if I had two clusters which are well separated, but are on line segments, but they're parallel line segments, maybe a little bit around them. If I were project to the side where they are very concentrated, it would be much more concentrated than a sigma because sigma comes from the length, then it would not recognize these two clusters.
That's right. I mean, yeah, so you need the sigma separation otherwise. Right. So what can happen here is you have the well-separated case, let's say two Gaussians. Right. As you move them closer, right, they will stop being well-separated at some point, and you move them even closer, they will satisfy anti-concentration because they'll become one.
But I just meant that it's different in different dimensions. I could have something that is geometrically well separated, this joint is right. One. But if one extent is much longer than the other, then kind of the criterion that comes from this sigma is applied to the side.
Okay, yeah. I see what you mean. You're referring to the pancake problem, which is if you have two pancakes with very large sigmas here, very large sigma.
Yes.
And this does not handle pancakes.
Right. Okay.
No.
This
does not. Now, we don't know how to handle pancakes in any generality. We only know for Gaussian.
I just try to understand what this means.
Sure. Yeah, it doesn't handle. We don't take the sigma, directional sigma, as a separating parameter. We take the max sigma of the component. Though of the component, that's important, not the max sigma of everybody. So here's another version. This is also satisfied by two Gaussians against one. So a set S of data points is from one cluster, if you will. If it is from one cluster, the following is true. For every subset, ignore this, for every subset, the subset sigma is not much smaller. It's at least 1/12 as big. You do need the scaling factor as well. Okay. So this says that I'm pretending to be a cluster, I better not have a large subcluster inside of me. The lemma, which also requires a little bit of work and some VC type Vapnik-Cherenkov based argument, but it's easy to show, not difficult to show that anti-concentration of the last slide implies NLSC. NLSC is weaker. So here's the main theorem. Now we are ready to state the main theorem. There's a polynomial time algorithm which given data with a ground truth clustering, which is nice. So it satisfies mean separation, it satisfies minimum weight, and NLSC, no large subcluster. This is weaker than anti-concentration, right? So each cluster has the property that it satisfies no large subcluster. No subset of it is much tighter in spectral norm. By the way, it's very important that you work in spectral norm. If you work in Frobenius norm, none of this is true. And then it finds K exactly and GT approximately, which is what we are seeking to do. Now, corollary, so you asked me this question about stochastic. So if you have a stochastic mixture generating the data, now we assume, let's say, anti-concentration. NLSE is enough, but now we assume anti-concentration of the PDFs. Okay? And we assume mean separation and minimum weight of the components of the mixture, of the generating model, population, assumption on the population behavior, right? We can find K exactly and GT approximately, provided, and here comes the statement about the number of samples. So you need this large number of samples so that the first and second moment empirically or close to the first and second moment of the population. Otherwise, you can't apply this, right? So I'm making assumptions about mean and standard deviation of the PDFs. And I need to, for the algorithm, I need mean and standard deviation conditions on the empirical data. And you only get that if you have large enough amount of data. Right? But large enough, so here's a difference between TCS and statistics, perhaps. In statistics, learning a stochastic mixture means you get all the parameters of the distributions. I don't mean that. I mean you cluster the points correctly. And then it's again somebody else's department to go find the parameters. It's not mine. But we need here samples enough only to get the mean and standard deviation right. So if you have a general Gaussian in D space, the sample complexity is D squared to do parameter learning. I'm only going to insist on D so that you get the mean and standard deviation.
I'm really confused with the difference between this NLSC and the one that I forgot what you called it, but the one that ensured identifiability. Isn't the result above saying that NLSC is sufficient to actually get identifiability of K?
So identifiability involves an exponential time algorithm. This result is polynomial time, right? Is that the question? Or?
No. Well, okay. What I'm saying is this recovers K, right?
Yeah.
I think there's only one K.
Absolutely correct.
Only one K with a weaker condition, so I just don't understand the point of the.
Oh, I see. So why did I put up identifiability at all?
Yeah.
Right. It's just a build-up term. Yes, you're right. This implies identifiability.
Okay.
There's only one K. And it implies also that the CL or model is right because I get the ground truth. You're right. There's a stronger theorem than identifiability. I think I put up identifiability to say that even identifiability was not known before. That given data, you can pin down K. The proof is simple in the paper, so that we did that. So you need to get the first and second moments right, then the clustering can be done. For log concave mixtures, you don't need to explicitly assume anti-concentration. It's true. All log concave PDFs, certainly Gaussians, you know, 1 over root pi sigma is set up as a giveaway, but it's also true for log concave. It may be 4 over. So any log concave PDF point-wise is at most 4 over sigma. Where in any one-dimensional projection where it's a sigma of that one-dimensional projection. That needs a proof, but it's known. So is the main theorem clear? So I think I'm going to, let's see, I might have about 10 minutes left, according to my reckoning.
You have even more because we started late.
Okay, no, I'll finish. I mean, I'll finish on time, the 40 minutes. So, so this is the main, the determinant. This is deterministic, and this is just an application of that. So I'm going to try to describe the algorithm. I was going to try to take so much time for the motivation that we don't get to this, but we did get to this. So we'll describe the algorithm. So I'm going to describe first the algorithm violating what I said, that only the data is given. I'm going to assume W naught, the min weight of a cluster, is given. That's much simpler, and it's a subroutine for the other thing. So I might as well state that. So if I take a set of data points which minimizes sigma, subject to this cardinality bound, we can show that it's essentially contained in a single cluster. So if I can find such an S, I would have found what we can call the nucleus of one cluster. Then here's an attempt at an algorithm. Find such an S. Peel that S off. and then repeat the process, and you might get S from a same cluster or different cluster. It's got to be in one cluster, basically. If we show that if S is close to one of the already found S primes, then it is from the same cluster as one of the S primes. We have to prove this. We do prove this. The important thing is these are data-driven quantities. They are not extraneous things. And at termination, we prove that you get exactly K. So K is the correct number of clusters. You get that many S's, so you count them, and that's your K. Okay. It's also true, afterthought, the nuclei can be used also to grow the actual clusters. You can do the clustering problem besides determining K. Now, very important again, all steps use quantities determined by data plus W naught. The star contains some W naughts, but it's all known to you from the data. No extraneous quantities. Except for step 2, this step, all are doable with some technical work. All these statements are true. I won't prove them. Now I'll focus on step 2, and I'm going to take a few minutes to describe step 2. It's because it's an interesting problem in itself. I want to find sigma among subsets of a given size, given some data. It's NP hard, as you can imagine. But what we give is a bi-criterion problem, which gets the size of the set and sigma both approximately correctly. Okay. That is, we have a polynomial algorithm which finds, we can fudge both these quantities in a way I won't describe, polytime to find K given this W naught also. And this is used as a stepping stone to the other one. So this is the exact factor. Don't worry about that for now. And this uses semi-definite programming. I'm going to spend a few slides on this. Spectrally tight subsets, independent problem, given a set of points and an alpha, find an alpha fraction so that the sigma is, now sigma is related to the this is spectral norm for matrix A, whose columns are data points offset by the mean. This is not difficult to see, but we'll assume that here, right? So I just have to find a spectral norm calculation, which I know how to do. If we had Frobenius norm, it would have been much easier, but it won't do the job. Okay, so.
Over there.
Oh, yeah, it fell on the
Yeah.
floor.
Or it fell down. Yeah, so I want to do at least strike one connection before I quit. Expander graphs come in here for spectral norms. So okay, so here's how they come in. So sigma is just a spectral norm of that matrix, data points offset by the thing. Now the mu s is an annoyance because I don't know what it is. So instead there's another definition, which is pairwise. Take the difference between every pair of points and take the spectral norm of that matrix. You have to scale it a little bit. Okay, so let's look at this sum. I take data point I minus data point j and use an arbitrary vector and take the dot product squared, and I sum over all ij. Now here's a very crucial observation. If I have an expander graph with one vertex per data point, that does something for us. What does it do? There's something called Cheeger's inequality. So a bunch of you are rapid mixers, you know what's going on. Otherwise, I won't have time to describe it. But Cheeger's inequality tells you that for every unit vector, the star, where the sum is taken over all ij, is upper bounded when I take the sum only over the edges of the expander. Instead of taking all pairs, I need to take only the edges of the expander. So a spectrally tight subset can be found by just constructing an expander where the sum is small, expander graph. Now that seems difficult, but there's another line of work. It goes back to Layton and Rao, which says, basically proves that every dense graph contains an expander. And in fact, it can be decomposed as a union of expanders. It's also used in clustering. So we need to can substitute expander by dense in 5. So we need to find a dense graph for which the sum is small, but only over the edges. And so here's the semi-definite programming problem. I wonder if Okay, so one of these constraints ensures this dense graph thing. And again, maybe I won't do that. Okay, getting by with just data, W not given. I'm going to try all possible minimum weights. One, they come down in 1 over n, multiples of 1 over n. I try all of them. When we hit the correct W naught, the previous stuff told us K would be found. But what can go wrong before that? I'm going to give you an idea what can go wrong and not so much how to fix it. Recall our algorithm finds nuclei of clusters. There are 3 possible failures. Some nucleus has significant parts in 2 different clusters. So the ground truth clustering, 2 different clusters contribute significantly to 1 nucleus that we found. That's a problem. 2 different nuclei make it large parts of a single cluster. That's a problem. And the last problem is one of the clusters may have been left out of all nuclei. But these are the only problems. Why? Here's a statement. Negation of 1. 1 says some nucleus is significant parts of 2. Negation of 1 says each nucleus has at most 1 CL part. Must have something because it's not empty. Therefore, there's only 1 CL. So that says that. And negation of 2 and 3 says the converse. Each CL is a unique nucleus. So there's a 1-to-1 correspondence between clusters and nucleus, and therefore you find the correct number. So there are 3 failures to fix. Failure 1 is actually just NLSE, fixes it. Failure 2 will not happen. Failure 3 is actually more complicated, and I won't have time to describe it, but it's done in the paper. So I have the last slide, then I think I'll end on time. In practice, so finding K, this is a very, there's a first polynomial algorithm, but it's very expensive because STP is expensive. And more than that, the separations are high and everything is polynomial, but high. Faster algorithms, other applications of spectrally tight sets. I'll leave you with that. Maybe this I will mention in the open problem session later, if necessary. So that's it. Thank you.
So I actually didn't get the high picture when you cannot find W0n exactly.
No, correct.
Right. So any approximation of that should actually imply, like if you have an epsilon approximation of that, it should, I thought that it should imply 1 plus epsilon approximation of K.
So, okay, 2 things. 1 plus epsilon approximation of K is not good enough, right?
Right.
Okay, that's one problem. But the other problem is, I think it may be true what you're saying, that if I give you W to 1 plus epsilon, then I might be able to find the correct K. But I don't know that that is, I don't have a proof of that. W approximately may be enough, but I don't know that.
Okay. But I couldn't get why, even if, because you're peeling, right? So you find a nucleus, you peel, and you continue. If you cannot get it correctly, then you are going to peel more.
No, because the peels are just nucleus of the clusters. I'm not peeling the whole cluster off. Right?
Okay.
It turns out I can, but that requires the extra work. That is fixing 0.3. So it gets more complicated.
Okay.
Are there other questions? I had a question, but you mostly answered it, and it was about, in some sense, what happens if you do not have a problem for which all of these assumptions you're making are correct, and you said there is the issue of identifiability, which you need exponential time to even determine. But is there any? Do you have any intuition about when you drop any one of the assumptions, whether the algorithm would still do something reasonable, or is there like just nothing that can be said?
So it's possible, I don't know, but what I do know is there are worst case examples where the algorithm will fail under dropping one of the assumptions. So they are in the paper. So, but these are worst case examples. So maybe it's true that mostly the algorithm will do something good. That may be true even without all the assumptions. I'm not sure.
I see.
I suspect it's tough. It can be, so because.
It sounds kind of difficult, like if you dropped anything, the
Yeah,
problem
if you
might
drop any
become-
assumptions, I would suspect it's tough.
Thank you very much. Let's thank Ravi again.
Thank you.
So let's do just a slightly shorter break. Now it's 10:15, so let's all be back at 10:22. And after the next talk, there will be a longer break. So see you all at 10:22.
Oh my God. Which one? I think the next speaker.
So if you take the clear aspect from the algorithm, it back into the classical algorithm, we don't recover the same process.
No, you do. You do the correct classification. But very few classical algorithms work under this kind of weak separation. They usually assume the maximum sigma of all the components. They use that for separation. Except Gaussian. For Gaussian, this one. For instance, for Gaussian, you can put the state in.
So then I follow the line for k means, it is not true that data from the k means I mean that the optimum k means.
So that is just the constant.
We have to be bound. Sorry.
Just two things, right? One means. So if I take one mean and find the optimal solution. If I take two means and I take the optimal solution.
The balance condition, right? It's part of the.
So all I'm saying is
Then
one means
it's
is
reasonable, right?
right?